All right, we're starting.
Questions on the homework?
12, if you number 5.
What is number 5? Show how to obtain the probabilities listed under the theory column in table 10.2. Okay, so the sum, probably tossing a sum of 5 with 2 dice. We actually did this already. We did that whole table thing. We already did it. You toss 2 dice. There's die 1 and die 2. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. You're looking at the sum. So the sum was 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 8, 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. So if you're looking for filling out that table, the sum, they have the sum, they have the frequency, they have the relative frequency, and they have the theory. But in theory, what the relative frequency should be. Right? Which, so, for example, if the sum was 2, then how often does a 2 show up? Only one time. How many possibilities were there? 36. So this would be 2 out of 36, which would be 1 out of 36, which is, it's that, right? 0.0278. That's it. And you continue that same way for everyone else. So when the sum is 3, 3 shows up twice. So that would be 2 out of 36, which is going to be whatever. And you just do that for everything. What?
It was very peculiar.
What was peculiar
I
about
thought the wording was just like, what? But I gotta know.
it? Okay. What's the other problem? What's the other? What was there another
Did you
question?
ask for 12? I did, but I don't need help anymore. 12.
You don't need help anymore?
No computer.
Is there anything else?
Number 9. 9 and 15.
In 9, suppose the probability of being killed in an auto accident in a given year is that. Given the current population is this, how many auto fatalities would be expected in a year? Okay, so this is 9. Probability of being killed in an auto accident. This is the circle of life.
Your math department has a theme.
0016. We know that the population is 270 million at this time of this writing, roughly. So how many accidents per year? Fatal accidents per year.
How do you multiply?
for a year. Well, for that, you just know the probability is going to be 0.00016 is equal to some number of auto accidents over 270 million. And you solve for x, which you multiply 270 million by that, and what would you get? What? 43,000? Yeah, that's it. Because remember, the probability is just a ratio. How many times the thing happens that you're looking for out of the total possibilities.
So the 43 is this real data?
I don't know. And 15, in example 10.13, that's the birthday thing. 10 people in a room, probably at least 2 of them have the same birthday, In example 10.13, we determine the probability that in a group of 10, at least 2 people have a common birthday. Find the probability that in such a group, at least 1 person has the same birthday as yours. We actually did that example in class. Suppose there were 25 people, compute the probability that there are at least 2 people with the same birthday. Yeah, it's this, again, we did that in class. It's the same thing, except you do 25.
Yeah, I think we did it wrong.
Which one?
For 8.
What did we do?
So if it's the same as mine, you're gonna get the opposite, so which is none has the same as mine.
Yeah, so we're doing 25.
Yeah.
None of the 25.
It's 10.
So you find probably that none of the 25.
But A is 10.
It's 10. It's 10.
A is 10.
Oh, it's 10.
C is 20.
None of the 10 have my birthday. Yeah, what was that?
So what we did is 364 times 363 and so on and go down, right?
Yeah.
I think it's supposed to be 364 9 times. So like 364 times 364 times 364 so on. Because the only
We don't want them to have over 11 birthdays either.
I mean, no, it's only my birthday.
Right, so, yeah, assuming we don't care if any of the 10 any of the other 9, right? Because we're one of the 10, right?
Yeah.
Any of the other 9 have the same birthday. Then yeah, it would be 364 over and over and over, right? Because it doesn't matter if this person has the same as that.
That was the question.
And this is 9 times over 365. So this would be 364 over 365 to the 9th. And so probably that at least one has my birthday. Is just 1 minus that. Right, which would be whatever. Yep. Because I don't care if any of these guys share the same birthday. So if he has 364 days, the other person could be born on that day. I don't care. I just want to avoid my birthday. Right, and then you do the same thing, except now you do it like 25 times or 24 times in part C. So what was the answer for part B? Just for comparison, I think you did it.
Or just how we did it, like 364.
Yeah, but the actual number, what was the number?
0.064.
0.56.
0.56? Okay, yeah, so the probability is like there's a 56% chance that in a group of 25, 2 people share the same birthday. Yeah.
15B?
Mhm.
Yeah. In the back, the answer is a little different.
What does it say?
0.064.
That's for C.
That's for C. Oh, okay. Never mind. I forget. For C.
see, but I don't.
We should try with 40. I don't know if anyone did 40. Yeah, but it probably is more than a half that if you have 25. Any other questions here?
No, okay.
Can you go over that real quick? So you did 364 over 365 to the 9?
Yes, to the 9th. Because this person gets 364 out of 365, 364 out of 365, so on and so forth.
Okay.
So 365 happens 9 times.
So out of 10 people, you're included in those 10 people?
Yes,
Okay.
which means I'm only looking at the other 9 people now.
Okay. And how do you get, they got 64%?
64% is the answer to the other part. This is part A.
Oh.
64% of the answer to something. Okay, let's move on. Well, we're pretty much going to wrap up chapter 11 now. There was just like one example we wanted to do in there.
So funny. I want to be
So last time we spoke about conditional probability. What was this? What's the notation for it?
Oh, it's A.
straight line B.
What do we call this?
Probably A occurs given B occurs.
Given B.
Correct. Probability of A given B. Right? So that means probably that A will happen given that B already happened. What was the formula for it?
Probability of A and B divided by the probability of B just means that it's probability.
Okay, so that's the answer. Now, if the events are independent, then this guy becomes a product. The B's would cancel. You just get probability of A.
Yeah.
So it's not affected by B at all, right?
No.
But remember, there's no general formula for probability of A and B. It depends on the situation. There's only a general formula in the case that our events are independent, like one does not affect the other. Okay, so we spoke about that. Now let's actually just jump into an example.
And
Yes.
No.
I believe this is similar to a problem taken from the book, actually. College freshmen are required to take courses X and Y. You know that 50% get an A in course X, 10% get an A in course Y, and 23.5% get A in one or the other. So here are the questions. A. What fraction get A's in both. We're expressing B. What is the probability that a student that gets an A in course X will also get an A in course Y? C is receiving an A in X independent of receiving an A in Y. Justify. Okay, so 50% get A in X, 10% get A in Y, 23.5 get an A in one or the other. What fraction get A in both? Was probably the student gets A in course X will also get an A in course Y, and is receiving an A independent between courses. Okay.
Because of the information given.
Come again?
I understand that 15% get an A, 10%. What about 22.5% get an A in one or the other? What is that saying? I thought you're already saying that 15% get an A.
What would this be? So let's actually do this notation and then see what we're talking about. So let AX be event student gets an A in course X. And let AY be event student gets A in Y. So now what is this piece of information telling me? 15% get an A in course X. What is that saying?
AX is equal to
What?
AX is equal to 15.
No.
Probability of AX equals 0.15.
That's what that sentence tells me. It tells me the chances of getting an A in course X. What else? What does the second part tell me? Tell me the probability of AY. Well, that's just 0.1, 10% chance. What is this one telling me?
Probability of A plus
Slash.
A.
Probability of AX
A slash A.
or
A slash B.
Probability of AX what?
or AY.
Or AY, which is not plus. We only say it's plus if they're mutually exclusive. We don't know they're mutually exclusive. In fact, here we know they're not. There's nothing that say you can't get an A in both courses, right? So it does not translate to plus. We don't assume this. This is 0.235. I say get an A in one or the other. That or is there. So it's just probably of AX or AY. Okay, so now, given that information, so we basically read this work on to get the probability of each event, right? Once I name them with a variable. So I have all this information. So part A says, what fraction get an A in both courses? So in A, what do we want? What are we being asked for?
Probability that AX
And AY. Right, so that's what we want here.
Yeah.
Okay, so how do I find that, given this information?
you multiply the probability.
No. Remember my warnings. You never assume and means multiply. Only in a particular situation. If they tell you it's independent, then you assume multiplication. We have no indication that anything is independent here. How do we find A and probability of AX independent? Come again? Why?
They are independent.
Huh?
They are independent.
How do you know?
Because there are two different courses that have nothing to do.
What if one is a prerequisite for the other?
You're taking them both freshman year. One can't be a prereq if you're taking it at the same
Yeah.
time. You would have to pass the prereq to take the actual course. Well,
What do you do?
It's not prerequisite because freshmen, they both take it at the same time. If it's a prerequisite, I don't know. I'm guessing.
We can figure it out with this information.
Really?
can
So
you?
you're gonna hint us? That's what you suck.
There's an equation for it, there's a rule.
It's only years.
So,
Yeah,
what, do you have,
We have
This
to
is not a conditional probability.
no, it's independent.
You have like the result like A given.
Oh, wait.
The thing is, part C asks about independence, which means it's not obvious, right? It's not something, oh, it's independent. It's actually a part of the question to tell me whether it's independent or not. Maybe there's an equation that relates all of these together.
And you gave it to us?
Yeah.
Last week, the equation you gave us was, it's just equal to P of A. Because it was P of A times P of B over P of B. And the two P of B's canceled out.
Law of disjunction, probably if A or B is equal to what?
P of A plus P of B
Oh.
minus P of A and B.
We have an equation that relates all of them, right? So this means that P of AX or AY is equal to P of AX plus P of AY minus P of AX and AY. This is the guy we want. I know the values for everyone else. I know that this one is 0.235. This one I know is 0.15. This one I know is 0.1 minus the probability of the and. And so P of AX and AY will be, I take this 0.235 minus 0.15 minus 0.1, which gives me what? What does that give me?
Negative number? With a negative. You get negative.
Oh, I moved this,
Okay.
so this is minus and those are plus. I moved this to that side.
Will it be positive 0.015?
0.015.
Mm-hmm.
Okay, so this means the fraction is 15 over 1,000, which you can reduce, but whatever. Get an A in both.
It's like 1.5.
So at that point, we made a mistake here, but you saw your answer was negative, right? And we know it probably should never be negative.
Yeah.
So once you see you got a negative, you made a mistake somewhere, just go back and find it, right? Don't write down a negative number, because that's the worst thing ever. Okay, let's find the second problem. What is the probability that a student that got an A in course X will also get an A in course Y? This means we know they got an A in X. What's the probability that they get an A in Y? So in B, what do we want?
No, I did. We have to multiply.
So what do we want? In terms of math notation,
we multiply the probabilities. So
What do we want here?
probability of AX,
Probability of?
A,
No.
anything.
We want the probability that a student will get an A in course Y given that they already got an A in course X, right?
Is it A, Y, absolute value sign, A, Y, A, X?
That's what we want. Okay? Now once you know that, that's going to hint you an equation, right? We know that this already happened. They already got an A in course X. I want to know, given that fact, what's the probability they get an A in course Y? So what is the probability here? Probability of AY given AX is equal to
Probability that A and B, I'm sorry,
AX and AY over
divided by B, the probability of AX.
AX. So this I just found in part A, that's 0.015, over probability of AX I had from the beginning, that is 0.15. Which is?
No, no.
Which is what?
Is it 0.1?
So that's the probability that you'll get an A in course Y, given that you already got one in course X. Now you can answer the question, are they independent?
Well,
Yes.
How do you know?
It was a 50% probability I was right. So I just went for it.
Well, we don't need to take chances. We're not like daredevils or something.
We can put on the equation, and so if we got AX and AY is the same, like the same number as we got, then it is.
Okay, when I first defined what independent means, what's the equation I gave you?
so the probability of AX times the probability of AY divided by the probability of AY.
When I first told you about independence, when I defined independent events, what was the equation?
P of A times P of B divided by P of B.
No.
No, P of A and B of
P of A and B is equal to what?
BA times B.
P of A times PB, right? That's what independence means, right? So now you don't know if this was true, but now you can check it because you have all this data. So if you take A and B, right, we actually found that to be 0.015. Now if we take this probability of A, what do we get? That was 0.15. If I multiply that by this one, 0.1, what is the result? It's actually 0.015, right? So it checks out. These are independent, right? That's using the definition of independence. This is what it means to be independent. So I could just check that equation. An alternative would be, or, I also know that A, B are independent if the probability of A given B is equal to what? Just the probability of A in the first place.
Yeah.
But now I know the probability of A y given AX. That's actually equal to 0.1, which is actually equal to the probability of AX, AY, from the beginning. So that also checks. So you have two ways you could check this here. You don't have to guess and take a 50-50 chance. You just use the equations. There are two ways to interpret independence. Either this will happen or that will happen. Right? Once you know that the probability of and is the product of the probabilities, that means independent. Or if you know this conditional probability is just the probability of the first guy, that means independent. Right? So here we did a conditional probability. I got 0.1, which happens to be the probability of the first guy. Right? So that means they are independent events. So yes, they are independent. You have to remember those equations. They're very, very important. Yeah. So I'm not going to do an example about this, but I just want to mention it. We don't really do it a lot in 209. I've never actually seen anyone test it on it, but it's a pretty important theorem, so I thought I'd give you the equation. It's called Bayes' theorem. And it gives you an alternative definition for the conditional probability, just in case you have it, just in case you need it. This is P of A given B is P of B given A times P of A over P of B given A, P of A plus P of B given A complement times P of A complement. It's a very important formula, not really emphasized in 209 at all, but it's still a very important formula. I'm not sure if I assigned it as a homework problem. Let me see your textbook. Jeez. Oh, come on, come on. Let's be quick. But usually situations that have to do with like something like infection, where you can have something or not, you would use something like Bayes' theorem. Yeah, like maybe problem 16 would use Bayes' theorem. Problem 18 would use Bayes' theorem. I'm not sure if I actually assigned those as homework though. Problem 20 would use Bayes' theorem. Right? Basically it's when you want to find a conditional probability, but you don't know the and probability, right? You don't know how the probability of both happening together. You can sort of get around it if you know this information. I don't remember if I assigned it for homework. For problems like that, you can use something like this. That being said, we are going to move on. So that's chapter 11. That's everything we need to know for chapter 11. So the next test, of course, next week, Wednesday.
So you're not having an example of Bayes' theorem?
No.
Are you gonna test this on Bayes' theorem?
I just mentioned some problems. You can try them on your own.
Yeah, that
For
always
fun?
helps.
For fun, yeah.
Going blind and everything.
Now we're just going to do some random stuff. Yeah. Chapter 13. We're skipping chapter 12. It's not in our syllabus. But you might want to read it anyway because it's about genetics. But you don't actually do it. So all those people who are like really into genetics, you can go read chapter 12. We're going to move on to something called random variables.
That blood typing problem is not accurate at all.
What? In fact, part 1 talks about discrete random variables, and we will move on to continuous random variables later on. Chapter 13. Okay, so
We're gonna do review on Monday, right? Or like, we ask questions that we need answers? We should.
Wait, is the exam
sure, we
Wednesday?
can do a little bit of Wednesday, next week Wednesday.
Yeah, so Monday review.
We do like 10 minutes.
Well, I probably won't spend the whole class doing a review, but I can review some of the stuff.
Okay.
Goes through the review problems on my website, and then we
Yeah.
can talk about some of them
Okay.
on Monday if you have
When we're
questions.
done, can we leave on Wednesday, or are we gonna have class
Yeah.
afterwards?
Class afterwards. Come
Last
on.
time
Then I'm not gonna see you guys for like a week and a half after
Oh,
that.
that's fine.
No, it's too long. It's too long.
Because
we're
I-
fully Jhevon.
Because
We got
Sienna can leave. She can leave.
At least you noticed me today.
Okay, let's start with a definition. Simple one, not getting too complicated. A discrete random variable is a variable that can take on specific values. Take on values x1, x2, xn in such a way we could get more specific, but I don't want to really get more specific than that. Just think of it as a variable that can only take on isolated values, right? So for example, maybe a familiar example would be like numbers. Think of the difference between the integers and the real numbers, right? So your integers can only take on isolated values, right? But your real numbers, they can fill in any gaps that you choose, right? Between any two real numbers, you can find another one. And between those two, you can find another one. You can never isolate a real number. You can't write them in a list. You can't do anything. But for discrete random variables, you can literally list every possible outcome, right? If you can't list every possible outcome, it's not a discrete random variable. So examples of such variables is, for example, ones that we've done, the number on the face of a die. Let x be the number on the upward face of a tossed die. Then x is a discrete random variable. It's random in that you can't really predict what's going to happen, but at the same time, you know it has to be one of only 6 values. There are 6 isolated values that this x value can take on, right? And one of them is guaranteed for any random toss of the die, right? So that's, so is a discrete random variable. The values of x are anywhere in the set 1, 2, 3, 4, 5, 6. There's a listable set of isolated values that x can take on. And for each toss, only one of these values is possible. Let's do the 2 dice toss experiment again and see what we can say about it. Another example. let x represent the sum of the upward faces what are the possible values for x? And their probabilities. So the possible x values are 2,
4,
3,
3,
4,
4,
5,
5,
6,
all the way up to
12.
12. So there are 11 possible values for x. Now what about the probabilities of each? Like if I say, what's the probability that x actually gives me a 1?
1 out of 36.
0.
Oh,
1 out of
0.
36.
That
Right?
would be 0 out of 36 because the sum would be 1.
2.
2. 1 out of 36.
Right, because 1 is not a possibility, so
Okay,
yeah,
that's
that
fine.
probably doesn't make sense. What's the probability that x is a 3?
2 out of 36.
2 out of 36. What's the probability that x were a 4?
3 out of 36.
What's the probability that x is a 5?
4 out of 36.
I'm sorry, what? This is the sum.
The sum,
probability.
yeah.
Okay.
Remember there are 36 possible outputs. And there's only one of them where the sum is a 2. There's only 2 of them where the sum is a 3. There's only 3 of them where the sum is a 4.
4 out of
There's
36.
4 of them where the sum is a 5. How many have the sum is 6?
5 out of 36.
There are 5 of them where the sum is a 6. And that's probably that x is a 7.
6 out of 36.
6 out of 36. What's the probability that x was 8?
5 out of 36.
5, it goes back down.
It goes back down, right? It goes up and then back down. So
So
probably
this
if
is high.
x is an 8 will actually give us here. This is also a probability that x is 8. This would be the probability that x is 9. This would be the probability that x is 10. This would be the probability that x is 11. And this would be the probability that x is 12.
Yeah.
Right? So this is a situation where I can tell you each of the values and I can tell you the probability of each of the values occurred. Now we like these kinds of situations. And if you're wondering why, what do you think I'm thinking about? Like, why would I call something like an x? What am I going to try to do here?
Independent of something.
I'm not sure what that means. Well,
Solving the video.
Something.
almost.
given Something.
What we're trying to do is we're thinking of functions. We're thinking of something as an x value, which is like an input, and we're thinking of outputs, which could be like a probability. So this is where we try to want to finesse in the idea of functions into probability, because we like functions. We all like functions. We know how functions behave, right? It also gives us an opportunity to start getting graphs in order, because inputs and outputs, we can plot points, we can graph stuff, which we know that helped us a lot in statistics, so why not use that in probability? So the idea is we want to get the idea of talking about probabilities in terms of functions. And so we can call x, which is going to be our input, we can think of those as the possible values, possible outcomes, and then we can think of the output of this function as probabilities, or relative frequency, if you want to think of it that way. Right? So that's sort of where we're going. So whenever we have a situation where we can do both, that's really nice. I can tell you what the inputs are, I can tell you what possible outputs are. Now I can start to do a lot of things with it. To make our probability more accessible. So one thing I can do is what's called a probability distribution. Know that phrase because I can ask you for that. I can say, find the probability distribution of this. It's called a probability distribution. And it's basically a table. So let x be a discrete random variable. With values x1, x2, is that what I call them? Xn and corresponding probabilities P1, P2, Pn, then probability distribution for x is a table listing outcomes with their respective probabilities. We usually list them as a table. It's one of our most efficient ways to do it. But of course it jumps easily to a graph. So, example, if x equals the sum of two dice, which we just did here, and I actually find the probability for this, this set of events, all you would do is this table. We usually list it horizontally by convention, I guess. So you write x and p of x. Right? So along the x, you write down all the possible values of x. There's a 2 is possible, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, so usually listed as a horizontal table. Your possible x values goes along the top, and the probability of each x value goes underneath each x value. So here I know this is 1 out of 36, 2 out of 36, 3 out of 36, 4 out of 36, 5 out of 36, 6 out of 36, 5 out of 36, 4 out of 36, 3 out of 36, 2 out of 36, 1 out of 36. This table is called a probability distribution. So if I gave you a question, I said, okay, let x be the sum of the upward faces of two dice that are tossed. Find the probability distribution for this experiment. You draw this table. That's what you do. Right? That's called a probability distribution. You tell me all possible outcomes and their probability, you put it in a table, you get what we call a probability distribution. It's how the probability is distributed among the possible outcomes. Another thing we can do with it, just as with statistics, sometimes the tables get too large and the information is not as accessible anymore, we can draw pictures. So we can also get what we call a probability histogram. Where we plot values versus probabilities of those values. So probability histogram for this guy would basically look like a histogram. But here, on the vertical axis, we're graphing the probabilities, and on the horizontal, the values. So I can say probability histogram for the sum of two dice. So this. And my possible values, sum would be here. So the sum could be 2, or 3, or 4, or 5, or 6, 7, 8, 9, 10, 11, 12. And on the vertical, I will put the probability. So the possible probabilities are 1 out of 36, 2 out of 36, 3 out of 36, 4 out of 36, 5 out of 36, 6 out of 36. So I know to get a 2, the probability is a 1 out of 36. To get a 3, probability is a 2. To get a 4, it's a 3 out of 36. To get a 5, 4 out of 36, to get a 6, so 5 out of 36, to get a 7, that'll be a 6 out of 36, to get an 8.
Are they supposed to be connected to histograms?
No, not for a probability histogram. Because these values could be events or outcomes. You don't really think of them as numbers technically.
Don't we call it bar graph then?
Yeah.
What?
One of
No, it's called a probability histogram.
What definition you gave us?
10 would be what, 3?
Yeah.
11 is 2. Like, it's not the scale anymore. Come on. Okay, 12 is like a 1.
Looks like a bell curve.
Looks like a bar.
What, a bell curve?
Yeah.
Yeah.
Yeah, it's almost a bell curve.
It is going to tell us useful information.
Yeah. It helps you access the data a lot quicker. Like here, now you know if you wanted to bet what the sum of two dice were, what would you bet on?
7.
Tell you right away, you know. And, you know, like if I gave you that table with 36 data values, you wouldn't be able to say that so quickly. You'd have to count it, right? Or imagine if your table was a lot huger, right? The picture just it tells you you can see right away what the best value is, right? So here you can tell that 7 is that's the highest probability, and it branches off going down. Right? So remember, just as always, our diagrams are just a faster way to access useful information that we need to make decisions. Let's do another example of a random variable. Let x sorry. A fair coin is tossed 3 times. Now here's how I'm defining my variable. Let x equal the number of heads obtained. Find a probability distribution for x. And draw a probability histogram. anti-dust chalk. What if it wasn't that? I'd be like covered. It's like chalk everywhere. This is the anti-dust.
It's the mark board.
We can probably fit it here. So let's look at the probability distribution. It's going to be a table. So here's our possible x values and the probability of those x values. What are the possible x values in this experiment?
1 over 2.
The possible outcomes.
And or no, man.
X is measuring the number of heads obtained, or the possible values for the number of heads you can get when flipping a coin 3 times.
1.
Really?
Is the number of heads.
Number of, you can get 3.
You can get 3, yeah. What's the smallest up to the largest?
0.
0. You can literally flip 3 times, get tails, so you get 0 heads.
Oh,
Okay? What's another possibility?
1,
You can only get 1,
2,
or you can only get 2,
or 3.
or you can get 3. Right? Those are all the possibilities for the number of heads you can obtain. Right? So these are the values that this discrete random value can take on, and it has to take on one of these values every time you do this experiment. So what's the probability that you get no heads?
Probably we get 4 heads. Might 1 minus that. So it's 1/8.
How do you think about it?
The probability of getting heads the first time is not or 1 over 6.
It's the probability that you got both tails, which is
Which is 1 over 3. 1 over
It's 8, so it's 0 over 8. No. So,
it's a half to the third.
Okay.
It's a
So
seven
what
over
is the
eight.
probability, right? It's the number of ways you can get what you want out of the total number of ways, right? What's the total number of possibilities here?
8.
It's a 7 over
There are 8 possibilities.
and 7 over
I got one thing right so far.
Right? Why? Because for each toss there are 2 outcomes. It's an experiment with 3 stages. Use the multiplication. There are 8 possibilities, right?
8. Yeah.
Okay, so how do I know which one has, how many have 0 heads as a possibility?
Well, you can count if you
Wait,
have.
you can do like that table. Like, there are many ways you can get to it, but probably the table is the easiest way here. I know there are 8 possibilities, 2 outcomes, so I can sort of switch heads, tails, heads, tails, heads, tails, heads, tails. We did this before. So here's heads, heads, tails, tails, heads, heads, tails, tails. 3 and 4. Right? So what's how many ways can I get no heads? It's only one way, right? I get all tails. So there are 8 possibilities. There's only one way to get no heads. There's 1 out of 8. Is this probability? How many ways can I get 1? Well, in this situation, I get 1, 2,
3.
3,
No, just 3.
And that's it.
So there are 3 ways out of 8 that I can get 1. How many can I get 2?
3 out of 8.
1, 2, 3. 3 out of 8. I'm always going to get 3. Only one way. I toss all 3. So that's the probability distribution. Oh, here's a question before we moved on. What if I missed one of these? Like I did some other way, I didn't do it systematically in a table, and I tried to think about it. and I missed this possibility, right? Like, let's say I neglected to see that, right? What would that mean? How would that change the table?
You would have one unknown possibility because you still know that there's 8 full possibilities.
What is this? This would change, right? I just got rid of one of these guys, right?
But it wouldn't add up to 1.
So I get 2, right? So that was going to be my question. How do you know you made a mistake or you missed something?
It doesn't add.
Because the sum of all possibilities must add up to 1. So when you do your thing, however you figured this out, and you do a probability distribution, and you realize that the sum is not 1, you made a mistake somewhere. You need to go back and check something, right?
That's so true.
So if I have 1 out of 8, 3 out of 8, 3 out of 8, and 1 out of 8, you add these all together, you get 8 out of 8. You get 1, right? So that's one thing I want you to remember. So you'll know if you missed something or maybe you're overcounting something. If you got something bigger than 1, that's equally as bad, right? The sum of all probabilities must be 1. If it isn't, check your work. You made a mistake somewhere. Okay, so now that we've done that, let's move on to the probability histogram. Probability histogram for the 3 toss. So here is our x values. It could be either 0, 1, 2, or 3. I can either have a probability of 1 out of 8 or 3 out of 8. And this is the probability. So 0 can happen 1 out of 8 ways, 1 can happen 3 out of 8 ways, the other can happen 3 out of 8 ways, this can happen 1 out of 8 ways. Alright, so that's the probability histogram for this situation. So sometimes I'll just describe a variable in terms of words, and you have to figure out a way to count how many total possibilities there are and how many possibilities for each outcome to make this table. Right? So not always is the table going to be given to you. Sometimes you have to actually figure it out. Any questions on this?
There's none to it.
Jhevon, I have a question.
Yeah?
So when you do the possibilities, right? Like when you're writing out heads, 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 tails, tails, tails. Is there an easier way to do it than to go through the pattern?
You could do a tree diagram. You could also just list through the patterns in your head and try to figure them all out. There are usually several ways to get to it. You just find a way that's easiest for you.
If you gave us 4 times you flipped it, what would the 4th pattern be? Because this one is 1, 2, 1, 2.
Yeah, well, that would be 16. You'll still continue in the same way, right? You know it's 2 to the 4, so there are 16 possibilities. Heads, tails, heads, tails, heads, tails. Do that 16 times. Then every 2, every 4, every 8, every 16, every 32. It goes up by powers of 2. How many times you skip. Right? And if there was someone with 3 possibilities, you could do like skip every 3. So it's every 3, every 9, and so on and so forth.
Actually, can you explain how you did that? I know you were trying to, but it didn't happen.
If there are only 2 possible outcomes for something.
Okay.
To start off, you can alternate each outcome,
1, 2,
right?
1, 2.
But because there are 2 possible outcomes, to make sure you're hitting all possibilities, you jump by powers of 2. So after you do every 1, which is 2 to the 0, then you do every 2 and alternate, which is 2 to the 1. Then you'll do every 4 and alternate, which is 2 to the 2. Then you would do every 8 and alternate. Then every 16 and alternate. And if it's like every 3, you'd go alternate every 3, alternate every 9, alternate every 27. Right? You can build up, the table can get large. So, okay, so let me, it's kind of repeating that, but I'll repeat another dimension of it. The 0 to 1 principle is that there are two things that must happen in your probability distribution that you need to look out for. One, sum of the probabilities in the distribution must be 1, and second, each probability individually in the distribution must be between 0 and 1, possibly inclusive. But of course, if any guy is 1, it means all others, you have to have probability 0. Right, so these are two things you need to look out for when doing your probability distribution. Make sure each probability value is between 0 and 1, possibly inclusive. And when you add them all up, you should get exactly 1. If either of those do not work, it means you made a mistake. Or it means you're not looking at a probability distribution at all. So let me ask you this. Are the following probability distributions? So here's one. A, x, p of x. 1, 2, 3, 4 are the possible values of x. Probability 0.1. 0.45, 0.2, 0.5. B, x to x, 7, 12, 13, 19 are the possible values. The probabilities are 0.1, 0.3, 0.45, 0.15. Find y so that the following becomes a probability distribution. $7:30 already?
Yeah.
Oh.
Yeah, let's just leave early today, man. On the wrong day.
We already did anything.
Come on, I've
We
been
haven't
taking
done
notes the
anything.
whole
We're not
time.
gonna
No.
have time. I've learned so much. My brain feels like a
I
plate.
feel like I come in here and I just write.
You know how many pages of notes we have for chapter 13? We're still on the first page.
We'll save that for another day.
Okay, let's do this. What do we have here? Is it a probability distribution?
Yeah,
No,
no.
the first one isn't because it adds up to 1.25. The second one is because it adds up to 1.
If you take the sum of the probabilities, you get
1.25.
1.25.
Not one.
So that's not 1. So the answer is no, this isn't. What about this one?
Yes.
It is.
What's the sum of the probabilities? 1. And individually, each is between 0 and 1. So yes. Find y so that this is a probability
1/6.
distribution. So this, what did you set up to figure that out?
You know magic?
Magic?
Yeah.
Don't use magic, it's not allowed.
So if you add all the probabilities.
I should put that in my instructions, by the way. You're not allowed to use magic. Well, that probably falls under divine inspiration, which I have
Yeah, you
listed
have it
there.
in there.
And make
I-
it.
And yep, it's in
And
there.
make it
It says
equals
divine
one.
Right, you set it equal to 1. Yeah, divine inspiration would count as magic.
Okay.
And you pretty much subtract all these, you get y equals 1/6. So that actually works, right? That makes sense, that answer. What about here?
No.
Because these add to 5, 6.
Thinking that's a 2.
Yeah.
Yeah, it's a 3. So what is,
No.
how do you know? What did you do?
Because it's greater than 1.
What is it?
I don't know.
So you just add them all up. Y plus 1 plus y plus 3 plus y plus y plus 2 must be 1. So what does that mean y is?
Not 1.
Well, it already can be 1. You know that your y has to be negative to get back to 1. I'm adding 1 and 3 and 2.
You can't have a negative
Right?
possibility.
And to get back to 1, I need to be, y has to be negative, so I can find the exact, but did I actually look at the exact one? It was actually minus 5 over 4. So this would be minus 5 over 4 to get back to 1, so nonsense. Right? Because a probability cannot be negative. What about this one? Same thing.
Same thing.
Y plus 1 plus y plus 1 plus 0.1 plus y plus 0.9. We set that equal to 1. Figure out if that has an answer. Hopefully it's an answer between 0 and 1, and we're good. And this answer was minus 0.6.
Jhevon, I had a question.
Yep.
Are you sure you didn't write negative 6 over 4?
Nonsense. Negative 6 over 4 where? For this
Y
one?
is equal to, yeah.
Negative 6 over 4?
Because it's 2 plus 3 plus 1.
Add 1 and 3 plus 2. Right, so this here is 1 plus 3 plus 2, right? That's 6. And move it over, I get a minus 5. Then I have 1, 2, 3, 4 y's, and I divide by 4.
Oh, there's a 1 on this side. I forgot that there was
There's
one.
There's always a 1 on that side. You're adding up the probability.
Gotcha.
So.
And in this one, you add all these guys up, set equal to 1, you get y equals this. So to make this a probability distribution, my y has to be point. Is that nonsense?
That is nonsense.
Math is nonsense.
Is that nonsense?
Just kidding. I love math.
Let's see. 1 plus 1.
Well, minus 0.6 is less than 1, right?
0, 9.
So this would actually be positive. It would be between 0 and 1 here. Like if I put in minus 0.6, I would have what here? Huh? 0.4, 0.4, 0.1. Here I'd have what? Huh? 0.3. Do those all add up to 1?
No,
Did I actually do that?
0.8.
I have minus
You
0.6.
get 1.2
Yeah, 1.2.
I get 1.2 where?
as
If
the,
you add all of
if you add them up.
For the y?
Yeah, 0.4 plus 0.4 plus. If you add up the probabilities, you get.
Did you solve this for y? What do we get here?
Oh,
Oh,
we just trusted your answer.
so 1 plus 1 plus 0.1 plus 0.9 is give you 3.
Is equal to 1.
And then 1 minus this, right?
3y is equal to -2 over 3 over 3.
Divided by 4. So it's 0.5. Negative 0.5.
It would be divided by 3. There are
Y is
1,
equal
2,
to
3
negative
y's.
2/3.
What do we get?
Negative 2/3.
Negative 2/3, which
Yeah,
is like
which is 0.6666.
0.67 something.
Yeah,
Okay, so it's minus, let's actually write it as 2/3.
okay.
Two of your traits.
And so this would be what? Let's write these as fractions so we get the exact answer. So this would be
1 over 3.
1 over 3.
1 over 3.
This is 1/10, right? Now if I take 0.9, this is 9 over 10 minus 2 over 3. What is that? Is that between 0 and 1?
That is 173 divided by 3.
Well, it should be. It's like 0.6.
It's 7 over 30.
So it actually does make sense, right?
So it's not nonsense.
It's not nonsense. It's because Sayana shouted it out. Let me write it out. I guess we will stop there.
Oh my god.
So I have a test on Monday. That's good.
Monday, I think
All
that's
right.
Wednesday.
So later.
Wednesday.
Monday.